Good afternoon, everyone. My name is Aagya Dahal, and I am a PhD student at the University of Connecticut, working with postdoctoral researcher Ifai Wang and Dr. Kai Villa. So, Dr. Kai Villa is here with me despite his busy schedule in the conference, so I'm very happy. And the topic of my research is advancing sustainability in ultra-high performance concrete. And for that, we are using SCMs and we are enhancing the dispersion in the SCM. So I'll be talking about it. So we know that ultra-high performance concrete is very amazing material as it has high strength and durability. In order to advance, but the ultra-high performance concrete has the cement as the binder, which is creating a lot of carbon dioxide and causing carbon footprint in the environment. So the objective of our research is to reduce the carbon footprint by introducing supplementary cementitious materials. And we are not only introducing them, we are trying to disperse them properly in the pore solution. So I will be talking about it further. The big picture. So the big picture of our research is to create a sustainable and resource efficient UHPC. By sustainable and resource efficient, what do we mean? Sustainability is like reducing the content of the cement, and we want to reduce the content of the cement by introducing the supplementary cementitious materials, because they are like the industrial byproducts, and these materials are examples are silica fume, glass powder, fly ash. So we have tested these materials, but I already stated that these supplementary cementitious materials tend to agglomerate in the cement pore solution. That is, they tend to form clusters, and which reduces the reactivity of the UHPC, and also they do not give a satisfying performance. We are trying to incorporate PCE superplasticizer, polycarboxylate ether, which has the role of doing adsorption, and it ultimately leads to disperse the particles better. How we are doing is we are storing the pore solution by using different methods, which is by vacuum filtration and by squeezing apparatus. And then we are analyzing the pore solution by using different techniques such as sedimentation and microscopic techniques. We have further utilized the particle size analyzer to analyze the size of the particles, but I will not be discussing about the particle size analysis here because I think it will be too long. So I have just limited my presentation to sedimentation and microscopic studies. So extraction of the pore solution. So before we talk about extracting the pore solution, let us fully understand what does a pore solution mean. Pore solution is the liquid phase present in the pores of cement paste. So it may be either in the gel pores or the capillary pores, and they contain dissolved ions such as calcium, sodium, potassium hydroxide, sulfate. They are in the larger concentration, means like they are the major ions, and they also have some minor ions such as aluminum, iron, and magnesium. Why we are studying the pore solution? Because understanding the pore solution chemistry is pivotal as we tend to understand the key to control dispersion. Because if we understand the pore solution chemistry, we can clearly understand how the SCMs disperse in this solution and how the PCE reacts in the pore solution. So these are mainly extracted by two methods. One of the steps of our study is comparing the two methods, vacuum filtration and pressure squeezing. And then in the step 2, we tend to analyze the dispersion techniques of this SCM using the pore solution that we extracted from these two different methods. And in the characterization part, we study the pH and ion concentration of the pore solution. And ion concentration we are studying for different variations, like the types of the cement, the water-cement ratio, and those different squeezing pressures. So the materials we used are ordinary Portland cement type 1, type 2, type 1-2, and oil well cement, all conforming to ASTM. And silica fume, supplementary cementitious materials we used were silica fume, glass powder majorly, and we also used fly ash and limestone powder. We mostly used a water cement ratio of 0.4 for major part of our study, but we also used 0.7 and 0.55 for comparison. And for the squeezing, we only used water cement ratio of 0.2 because we are targeting our study towards UHPC, and the squeezing squeezing apparatus gives better results when we have low water cement ratio. But for one comparison, we did one sample with 0.4 water cement ratio for the squeezing as well. And when we added PCE for the squeezing, we added it 1.5% by weight of cement. So I'll be talking about the specimen preparation. It's very simple test. In the vacuum, we are using 200 grams of cement with deionized water, and those samples were mixed for 1 minute in Resodyne acoustic mixture at 90% intensity, and they were sampled after 30 minutes, and then for squeezing, we are using 300 grams cement. So there might be a question why we are using the different amount of cement for different process, because the squeezing has a relatively large cylindrical size, and the sample that will be sampled at the end of the process is relatively little. So we want to extract more sample with one test, because the test is very intensive, labor intensive, as the instrument is heavy. And we are mixing it for 3 minutes, because if we mix for just 1 minute, the paste will be relatively dry, and there is no proper mixing of the samples. So we are mixing it for 3 minutes. Let us see the comparison between the two methods. As I already stated, this is one of the major steps of our study. So vacuum versus squeezing. So you can see a schematic of the vacuum filtration. The vacuum filtration is a very simple technique that uses pressure gradient to separate the pore fluid. We are not using gravity filtration because it is relatively slow. So we want to use the vacuum filtration, and the vacuum range is very little. It's around 1.5 to 4.5 psi. So the quantity of the sample that we extract is if we do 0.7, we are extracting about 70 grams of water out from 140 grams of the sample. The extraction time is approximately 10 minutes, and we stop the extraction of the sample when we feel that all the solution is out and the paste is completely dry. And for the extraction, we are using Wattman number 8 filter paper for the first extraction, and we further filter that solution with Wattman number 42 filter paper. And for squeezing apparatus, you can see in the right side figure, there is a large steel apparatus. It's very heavy, and for the squeezing, we are extracting at pore water cement ratio of 0.2, and I already mentioned for comparison, we also extracted one sample at 0.4 water cement ratio, and the paste is placed hydraulically in cylinder, and we use 2 filter plates at the top and bottom of the specimen, each filter plate consisting of 7 filter discs, so that we get a very clean filtrate at the end of the sampling process. The measurement of elemental concentration was done by spectro across ICP OES. So we used inductively coupled plasma emission spectrometer, because it has very good results, and it can detect a very small amount of ions as well. So we determine the major ionic species such as calcium, sodium, potassium, and sulfur. And we also determine the minor ions such as aluminum, iron, and magnesium, but they had relatively very low ionic concentration. So I'll not be discussing about those ions in the result part, because their concentration was low, and when they were analyzed, it only showed beyond a detection limit. And the principle behind each is that each element emits light at characteristic wavelength when excited in plasma, and we got elemental concentration in millimole per meter. And then the next test we conducted was sedimentation test. This is a very simple test, yet it's effective. So for this test, what we do is we take the weighted amount of sample, with a known weight based on the bulk density of the sample, and mix it in about 100 ml water in a Resodyne mixture. Then we quickly transfer it to 100 ml graduated cylinder, and we note down the time for 1 minute, 3 minutes, 10 minutes, and 30 minutes, and let the sample settle without disturbing it, and visually capture the sedimentation rate by using the camera of the mobile phone. So it's very simple, yet it's a measure, but we cannot tell that it's very accurate or relevant, because it's in the sedimentation it's not just the effect, there are multiple effects such as viscosity as well. So to support this, we further conducted other type of test. So this is the sedimentation test for the silica fume. So I have only shown for silica fume, but we conducted for other SCMs as well. For the figure A, we can see in DI water. So we can see like the silica fume is settling like very rapidly, but in case of pore solution, it's settling even more rapidly, which shows that the ionic concentration of the pore solution leads to greater sedimentation rate. And when we add PCE to the solution, we see that the solution is stabilized and the sample height has raised. So we can say that like it's one of the tools that says us that in the pore solution, the particles tend to agglomerate. So the next test we performed was optical microscopy. It is a more directive way to measure dispersion or agglomeration rather than sedimentation. So for optical microscopy, we use Zeiss Axio imager, and we put a small drop of sample in a glass slide and absorbed it in the transmitted mode of the Zeiss microscope, and we saw these figures. So these 4 figures show the representation of the silica fume in different conditions. The first was in DI water, and in DI water we see the large flocculates of the sample ranging from tens of microns to several tens of microns. And in pore solution also the condition is same. So we see larger flocculated samples. And then when we add PCE to it, we see like the agglomeration has reduced substantially, but not to a greater extent that fully representative of the silica fume particles. So what we did was we introduced a physical method that is by ultrasonic treatment, because the chemical method alone did not work. So in addition to the chemical method, we incorporated a physical method of ultrasonic treatment and tried to disperse the silica fume, and it showed a significantly good result. So that's the reason whenever we mix UHPC, we always pre-treat the silica fume with some aggregates or some so that they are dispersed better. And the next is I want to point out at the pH results. The pH the pH results is basically the pH of the pore solution, and we are trying to see the pH of the solution in water to binder ratio of 0.7 and 0.4. And obviously we see that in water to binder ratio of 0.7, the pH is low. It's because of the dilution effect. So ignore the first type 1 cement, because there might be some error in the measurement or sampling issues. But in all others, we can see that there is a significant difference of about 0.01 to 0.05. Even though the sample is diluted, the pH is not very significantly affected. This can be due to the fact that when we dilute the sample more, there is more release of the ions, increasing the alkalinity. So therefore, the reduction is not very significant. And when we use the silica fume, the pH is significantly reduced, and we can see this has 2 things to do with it. One is the use of cement. The use of silica fume reduces the cement content. That's why the pH decreases. And another is silica fume is pozzolanic and consumes calcium hydroxide, so that the pH is reduced. Next is our elemental concentration results. So in the elemental concentration results, I have shown for 4 different elements: calcium, sulfur, sodium, and potassium. I already mentioned I did not include the minor species, though we have the concentration data of that. So in the left of the graph, I have shown the concentration for calcium only. So please don't be confused that calcium is higher than other, because the right side has higher concentration up to 500 and the left has lower concentration. So the right side is concentration for sodium, potassium, and sulfur, the calcium ion concentration is relatively low as compared to sodium, potassium, and sulfur in the cement pore solution. And we can see that type 2 cement has more calcium concentration than the other cements. It's because of higher C3S content in the type 2 cement. And the sulfur content is more in type 1 cement because of higher sulfur trioxide content in the type 1 cement. And the alkali content is more in type 1 than type 2 and then oil well. And for the pH and for the water to cement ratio of the cement, as we increase the water to cement ratio, the calcium ion concentration is higher. This has to do with the fact that as we dilute the sample, more ions are released so that we get higher concentration of calcium. Next, we have elemental concentration results for the different pressure and the vacuum filtration and the squeezing apparatus. And the next is for the same squeezing apparatus at different pressure ranges. So we can clearly see a trend in the vacuum filtration versus the squeezing. The calcium ion concentration has increased significantly. Like in the vacuum, it's around 5 to 6 millimole per liter, whereas in the squeezing, it's around 25 to 26, which is like 5-fold. So it shows that our hypothesis is that in the vacuum filtration, the larger pores are drained out, and in the squeezing apparatus, the smaller pores are drained out, so that the calcium ion is released from the smaller pores. So that's our assumption, and our assumption is consistent when we do the analysis in the different pressure ranges. So 20K here represents the force applied as 20,000 lbs, so which is equivalent to a pressure of 28.3. So there is a small chart. So we have applied a pressure up to almost 200 megapascals in the pressure squeezing, and we see a consistent trend of increase of calcium concentration. The other ions are not pressure sensitive, as we can see, like there is no significant trend or there is no significant behavior. And the next is the sedimentation test results. Like we have performed sedimentation test in DI water in pore solution and in pore solution with polycarboxylate ether, PCE, at different times. And we can clearly see that glass powder is very stable in DI water. But when we go to the pore solution, the glass powder has a rapid rate of sedimentation. But the other SCMs, they are almost same behavior in DI water and in pore solution, which indicates they are agglomerating in all the solutions. And when we introduce PCE to it, there is a significant reduction in the agglomeration, and the particles are dispersing better. This is also one of the proof that it's a simple test, but it's a proof that SCMs tend to agglomerate in pore solution, and when supplemented with PCE, their agglomeration reduces. So from this study, we get the following conclusions. The first is that pore solution chemistry depends on different factors such as water-cement ratio, cement type, and extraction method. Second is that sedimentation occurs rapidly for untreated pore solution, and we got a conclusion that PCE enhances the stability of the supplementary cementitious materials. And the other conclusion is that optical microscope proves an efficient method to support the sedimentation results. I would like to thank Schlumberger Foundation faculty for future for funding my PhD for 2 consecutive years and also funding this conference. And I would also like to thank Advanced Cementitious Materials and Composite Lab, ACMC UConn, for lab space and experimental support. Lastly, I'm happy to take any questions, and you can reach me directly at aagya.dahal@uconn.edu, and there's a QR code to my LinkedIn profile. I'm happy to connect. Thank you.